Glad to be here. Thank you for coming. And let me start by introducing my collaborators. I was very lucky to recruit three excellent graduate students, Mohammed, Ayush, and Jyotish. Mohammed and Jyotish are defending in a month or so, and Ayush has about a year left. Also, we have a visiting graduate student, Akif, visiting from Bilkent for 1 year. We had two great, excellent postdoctoral researchers, Emil and Julia, who was here for about 3-4 years, and Emil moved to industry, and Julia has a permanent position at Brookhaven, and Ezra recently joined. And here are some of my collaborators that contributed to this work. Antiy's group did a lot of the first principles calculations. Seth Tongai from material science did some of the experiments. I also collaborated with Yuan Ming Lu from Ohio State, Özgür Oktar from Bilkent, and Roderick Mössner from Max Planck at Dresden. And the funding for this research mostly came from NSF and very recently from DOE. And if you have any questions, before I start, if you have any questions, please feel free to interrupt me, okay? All right, so condensed matter physics is the study of different phases of matter, right? But what do we actually mean by a phase of matter? So this is a well-known phase diagram of water, right? So here is pressure, here is temperature, and depending on the temperature and pressure, you can be in a solid phase, ice, or you can be a liquid or a gas, right? So these are three different phases of water. And it raises the question, what actually differentiates these different phases? So if you think about the liquid and the solid, well, for a liquid, the atoms or the molecules can be anywhere in space, right? It flows, the atoms and molecules can be anywhere. Whereas in a solid, the atoms and molecules have well-defined positions. They have to, in a perfect crystal, the atoms has to sit in certain positions in the lattice, in the crystalline lattice. So this defines a solid. So it means that if you go from a liquid phase to a solid phase, you are actually breaking a symmetry of the Hamiltonian, a symmetry of the system, right? So in principle, the interaction between the atoms and molecules does not restrict the atoms to sit at certain positions. So in principle, the Hamiltonian has a continuous translational symmetry, whereas in a solid, this is broken down to discrete translational symmetry, right? So this concept of spontaneous symmetry breaking is, in principle, how we define most of the phases of matter in nature. So these were pioneered by Landau and Ginzburg. And in crystals, we have translational symmetry breaking, but if for different phases of matter, for instance, if you consider magnets, we break time reversal symmetry, at least time reversal symmetry, we may break different symmetries as well in magnets. And in superconductors, something a little fancier, what is called the U1 gate symmetry is broken. Okay, so whenever we have a spontaneous symmetry breaking, we can define what is called a local order parameter. For instance, if we consider a magnetic system, at very high temperatures, the magnetic moments of the system are randomly oriented, right? This is what we call as a paramagnet. But below a certain temperature called the transition temperature or Curie temperature, a macroscopic number of the magnetic moments orient towards a certain direction, right? That's what we call a magnet. And in this case, if we consider some kind of a ferromagnetic interaction, we would have what we have at the fridge doors, right? We have a permanent magnet. And so how do we understand the local order parameter? If we write the 2-point correlation function, in the limit of the distance going to infinity, this two-point correlation function that you are used to from calculating in statistical mechanics can be considered as the expectation value of the magnetization at a point and the expectation value of the magnetization at a faraway point. So in principle, now what I do here does not really affect what happens at a different further away place. Right? So I have a local quantity associated with this spontaneous symmetry breaking. So this is in principle the spontaneous symmetry breaking and the local order parameters are how we define phases of matter in the context of Ginzburg-Landau theory. And in the middle of the 20th century, if you have these local order parameters, then all the low energy excitations of this broken symmetry is what actually determines the thermodynamics of the systems. For instance, in crystals, you have phonons. In magnets, you have magnons, which are spin waves. In superconductors, you have vortices. These are what determines the low temperature thermodynamic properties of the system. Let's say it's such as specific heat. Right? So what Ken Wilson and others like Kadanoff also has shown that if you have a second order phase transition, you also have scaling and renormalization group near the phase transition. This means that different types of phase transition, let's say a structural phase transition versus a magnetic phase transition, even though they might have very different type of order parameters, if they fall in the same universality class, they will have the same exponents, right? For instance, here, the correlation length at the transition temperature diverges with a certain power law. And this power law is only determined by what kind of universality class this phase transition falls to. So this paradigm is now called Landau-Ginzburg-Wilson paradigm. Of course, other people also have contributed it, but if we were to pick only 3 people, we'd probably just pick Landau, Ginzburg, and Wilson. And this is how we understand most of the phases that we see around us. Even so that Phil Anderson, who is one of the founding fathers of many-body condensed matter physics, and I quote, broken symmetry is the most profound concept in physics, right? So this is literally how we understand all the phases of matter around us in terms of a state that breaks the sum of the symmetries of the Hamiltonian, which gives rise to a local order parameter and its low energy excitations and its criticality near the phase transition. All right, so I've been telling you about this Landau-Ginzburg-Wilson paradigm. That's how we understand most of the phases of matter. But actually, this was our motivation to see what is actually beyond it. What is beyond the Landau-Ginzburg-Wilson paradigm? Okay. So that's what I would like to talk to today. And these are the topological phases of matter. Okay. So let me start by just showing you maybe one of the most impactful data in the context of topological phases of matter. So this is the integer quantum Hall effect. Quantum Hall effect, I'm sure you have heard in, I don't know, preschool. You take a two-dimensional electron gas, you apply a perpendicular magnetic field, and you measure the transverse conductivity, right? So you apply a current, but you measure the transverse conductivity. So you are measuring sigma xy. So the electric field is along the x, you are measuring the conductivity along the y direction in the presence of an external magnetic field that's perpendicular to the two-dimensional electron gas. So, this is a problem that many of you may be familiar with because of the Lorentz force. Electrons would not go straight, but will go along one side more than the other side, right? That's why you measure transverse conductivity. And in principle, in this case, this is the original data from 1980. You would expect to see the rho xy, which is the transverse resistivity, the inverse of the conductivity, would go linear. And what von Klitzig and others observed is that apart from this linear background, there are these plateaus, right? And these plateaus actually correspond to quantized conductivity. So here, nu is an integer. So this one would be nu equal to 1, nu equal to 2, nu equal to 3, nu equal to 4, etc. And this quantization is so exact that this is one of the best ways to measure the Planck's constant. It's quite remarkable because, it doesn't really matter how many times you repeat this experiment. If you have different samples, different shapes, different amount of disorder, this quantization is so exact that you always get the same answer. If this was a phase that has a local order parameter, then every time you measure it with different sample, you would measure something slightly different because of some different disorder value, some different shape, etc. But in this case, it clearly, if you observe it, you observe the same effect every time. So it tells you that it cannot depend on the local properties. It has to depend on the global property of the system. So, with von Klitzig, he got a Nobel Prize a couple of years after this observation. And the understanding of this phenomena came 2 years later by Thales and others. And this is also part of Thales's Nobel Prize as well. That the way to understand this, if you calculate this sigma xy transverse conductivity with a linear response, some simple approximation, we can show that it boils down to integrating the curl of what is called Berry connection. And here, this u of k, if you have taken any solid state class, this is the periodic part of the Bloch wave function, right? The Bloch wave function is usually this u of k times a plane wave. So if you take this Bloch wave function and see how it changes within the momentum space, and then integrate the curl of it, so this is usually called the Berry curvature, it tells you how many number of chiral edge modes you have in your system. Okay, chiral edge modes. Chiral mean that it's going only along one direction. It has handedness, and edge modes means that this metallic state is restricted to be at the edge. So you can see that this quantity is guaranteed to be an integer, and it does not depend on the local properties of the system. It depends on the global property, something that you integrate related with the Bloch wave functions throughout the whole Brillouin zone. So this is one example, but in general, the topology in condensed matter physics, or in general, the topology of a system of closed manifolds is related with its differential geometry through the Gauss-Bonnet theorem, where if you integrate the curvature, it is guaranteed to give you the genus of the system, mainly the number of holes that you have on your manifold, right? So this is the time people will tell you the coffee cup is equal to a bagel, right? Or donut. So in our case, I'm showing the Turkish teacup, which has no holes on it, okay? So this is the topologically trivial one. And this, you can see that the coffee cup has one hole, donut has one hole, and then I don't know what this is, but this has 2 holes. Any questions so far? Okay, very good. All right, so actually, when we talk about topological phases of matter in condensed matter physics, this is not just one thing, okay? And this may even be an incomplete list, but this is at least the topics that I know about, okay? So the simplest ones are the topological defects of an order parameter. So these are real space defects it can be as simple as disclinations in a crystal. Or if you have a superconductor, it can be vortices. These are the vortices of, I think, a high temperature superconductor. Or if you have more complicated order parameters, like magnetic systems, you can have other topological defects like skyrmions and Meson crystals. So these are topological defects in real space. And there are gapless phases which can be considered as topological defects in momentum space. So in this case, this is the band structure of graphene. You may have heard about it. It's a two-dimensional sheet of carbon atoms. And in this case, its band structure has 6 Dirac cones that are located at the special points in the Brillouin zone, at the edge of the Brillouin zone. So why are these topological defects? Because similar to the quantum Hall effect, if you integrate the Berry curvature around these Dirac or Weil points, you will get a invariant, a topological invariant. You will get an integer. Therefore, once you create these objects, it's very hard to get rid of them. Okay? So that's why the Dirac points in graphene are very, very stable. It's very hard to actually get rid of them. Another topic that people are interested in, these are called symmetry-protected topological phases. These systems are insulating in the bulk, but have metallic surface states. So the example I give about integer quantum Hall effect is one of them. So in this case, the bulk is a two-dimensional system and surface is its edge, right? The bulk is gapped and you have chiral edge states. But there are three-dimensional generalizations. For instance, the topological insulators came in 2004 or 5, where these systems can be three-dimensional, right? So the bulk is a semiconductor, usually a rather boring semiconductor. And then on the surface, you are guaranteed to have some interesting surface states. So these are the angle result photoemission spectrum of the surface states in bismuth selenite. This may be one of the, I guess, most famous RPES data where you can clearly see the metallic surface states which form a Dirac dispersion. And there are actually many, many different type of symmetry-protected topological phases. And in general, our ab initio theory works very well in these systems because these are in general very weakly insulating. So this does not require you to be a strongly insulating system. All these metallic edge states comes from the Berry curvature of the underlying band structure. And the last type of topological phase I would like to talk about, and in my opinion, the most interesting one, are the topologically ordered phases. So these systems are very strongly interacting. They have long-range entanglement. The ground state degeneracy depends on the manifold that they live in. And they have fractionalized excitations, which are in general anyons. So if you attended Frank Wilczek's colloquium last semester, he talked a lot about anyons, right? So he talked about anyons in fractional quantum Hall state. And since we don't really have pictures of anyons, this is the picture that I put. So you can think these quasi-particles, these excitations of the system to be these anyons. And if you braid them, meaning if you take one and move it, the other one around it, if you have a fermion or a boson, you get -1 or +1. But for anyons, you get a phase. And in principle, if they are non-abelian, you can get, if they are non-commutative, you can actually get a different phase. And in principle, this is one way to store information non-locally. So if you want to make a topological qubit, this is one way to do it. But we are very far from that. Okay? So no one actually is able to show any of this. All right, so I actually worked in all of this field in different, not all of it, but I worked on wire semi metals, some of this, some of this, some of that. Today, I am going to actually talk about skyrmions, Y-zone crystals, and quantum spin liquids. And the class of materials that I want to focus on are van der Waals materials. And if you take two layers of van der Waals materials, and if you twist them, you can see that you create a new pattern, a new long-range pattern. So this is the lattice of the first layer, the lattice of the second layer, and you can see that a new large-scale lattice emerges, right? So this new large-scale lattice is called a Moira pattern. And the reason I'm telling you about this is in 2018, researchers at MIT observed unconventional superconductivity if you take two layers of graphene and twist it. In this case, this is the carrier density, which is you can change by gating. And you can see that there is a mode insulating phase, which is a strongly correlated insulating phase. And around it, you get superconducting domes, very similar to other strongly correlated materials. So most of these, these Moira superlattices of van der Waals materials have now proven to be very, very powerful platforms for realizing very exotic physics. But most of these systems that people use are semiconductors or graphene, which are, if you look at the individual layers, they are weakly correlated. And when you twist them, you get this strong correlation effects. But what I would like to investigate is what if we, instead of taking two weakly insulating layers, why don't we start with two already strongly correlated layers and twist them and see how its properties can be controlled? And in this context, in the two-dimensional van der Waals materials, the two-dimensional magnets is a great platform for this because most of these systems are already mode insulating, right? They are already strongly correlated. And in principle, if we study the bilayers and Moira superlattices of these systems, we may learn something new. So my group has been working on this. Okay, before I go there, let me tell you a little bit about these material classes. Even though the first two-dimensional material, graphene, was isolated in 2004, it took over 10 years to observe magnetism in two-dimensional materials. So this is the first example, is the iron phosphosulfide. And then it took about another year to find ferromagnetism. And similar to other two-dimensional materials, two-dimensional magnets show high tunability with pressure, strain, and gating. So that's what is very advantages of two-dimensional materials over some bulk systems. You can tune their properties much easier. And I'll get to this, but one to the material alpha-ruthenium chloride is actually the most promising candidate to date to observe a quantum spin liquid behavior. It's also a van der Waals magnet. Okay. All right, so as I mentioned, we have been interested on this topic for the last couple of years. And we have two complementary approaches. The first approach is to consider systems where there's a long-range order, right? So we treat at least the magnetism semi-classically. Okay? So this type of systems are a lot more related with experiments. Okay, so actually some of the things that we predicted were later observed in experiments. And but in this case, the magnetism aspect is at least treated semi-classically. And our other approach is to treat everything quantum mechanically, but study more model-based systems. So mainly studying the quantum spin liquids. So this is our two different approaches. And today, if time permitting, I'll try to give you a flavor of both of the things. So I will start from the more related with experiments, topics, and then I will crank up to more theoretical aspects. Any questions? Okay. So I'll start with skyrmions. So let me describe what skyrmions are. So skyrmions are topological defects of two-dimensional magnets. So if you remember when I was showing you the 4 different classes of topological phases, this is the one on the top left, right? Topological defects. So why is this a topological defect? So the skyrmion is a spin texture, right? And if you look at it here, at the edges of the skyrmion, the spins are pointing up. And at the center, it's pointing down. And from the edge to the center, it's winding. It has a certain winding, right? And you can consider a mapping from a plane to a sphere, where the center of the skyrmion is assigned to be at the bottom, the south pole, and the edges of the skyrmion are assigned to be at the top, at the north pole. And if you do this mapping, you'll see that in a skyrmion, you will actually cover the sphere only one time, right? So this is its topological charge. And if you make small local distortions, this topological charge will not change. It will always stay as one. And in principle, this mapping, you can get any integer that you want. And mathematical way of saying this is the second homotopy group of order parameters that has 3 components are integers. Okay? But really, the way of mapping is from a plane to a sphere. And these are actually real experiments. These are the Lorentz TEM experiments. It shows the in-plane component of the skyrmion winding. So it would be the in-plane component, not at the center or the edge. And this would show, I'm not sure how visible it is, but it shows when you have many of these where this skyrmions actually crystallizes. As I mentioned, when you create these topological defects, it's very hard to get rid of them. So people predicted that they can be created, manipulated with external electric and magnetic field, and people are trying to make devices for memory devices, etc. And in general, skyrmions in many systems are stabilized by an external magnetic field and a special type of magnetic exchange called Jelshinsky-Moria interaction. And if you want to make a device, people usually use metallic multi-layers. I'm not going to go into details why you need that, but that's what is necessary to have the Jelshinsky-Moria interaction. So the question that we ask is, can we actually stabilize skyrmions in Moira superlattices? And here the key aspect is the stacking dependent interlayer exchange, which I will keep repeating. So we are interested in this class of materials called chromium trihalides, where the X can be iodine, bromine, and chlorine. And these materials in the bulk exist in 2 different stacking. And if they are in rhombohedral stacking, so they have a low temperature rhombohedral stacking phase and a high temperature monoclinic phase. An interesting aspect is, depending on how you stack these layers, the interlayer exchange is either ferromagnetic or anti-ferromagnetic. So the interlayer exchange depends on the stacking order. These are the interlayer exchange that's calculated by Antia's group, not for only 2 different types of stacking, but if you go from one to another, you can see that it can be ferromagnetic or anti-ferromagnetic. And you can imagine that if you actually take 2 layers and twist it, you will create this Moire superlattice. And within the Moire superlattice, some regions will look more like rhombohedral stacking, and some regions will look more like monoclinic stacking. As a result, you will have a superposition of all different types of stackings within your Moire unit cell. So Antia's group calculated this interlayer exchange within a Moira unit cell. So this is one Moira unit cell. And we found that the interlayer exchange within the Moira unit cell is mostly ferromagnetic, which is this blue color, but there are 3 different regions where it changes sign to an antiferromagnetic interlayer exchange. And if you go from chromium triiodide to bromide and chloride, this region becomes antiferromagnetic region shrinks. So what we did is we proposed an effective spin model for this system for both intralayer exchange within the plane and the interlayer exchange. The intralayer exchange is a pretty standard model, and the novelty arises from this stacking-dependent interlayer exchange. And we calculated the interlayer exchange parameters. Antius group calculated the interlayer exchange parameters. And next, my graduate students, Mohammed and Jutrish, use some classical minimization. We are solving these models classically. Solve these models using some classical minimization methods by mainly time evolving the Landau-Lifshitz-Gilbert equation, which is a technical detail that I'm not going to get into. All right, so this is the phase diagram. What you can observe is that at large twist angles, you have both layers to be ferromagnetic, whereas at low twist angles, we have one skyrmion at one layer and 2 skyrmions at the other layer. Here we keep one free parameter which depends on the substrate. So this we do our calculations as a function of this parameter. And in this phase, you can see that there is, so this is due to periodic boundary conditions. This is one skyrmion and this is another one. So there's 2 skyrmions on one layer and 1 skyrmion on the other layer. And the results are, even though it changes a little bit at the intermediate region with this D parameter, but these 2 limits are pretty robust. So why does this happen? Well, mainly when we flip one of these antiferromagnetic domains, we gain an interlayer exchange, but we are paying a domain wall cost. And by comparing these two, we can estimate a back of the envelope analytical estimation for this transition, which matches pretty well with our numerical calculations. And you can see that at the intermediate region, when these antiferromagnetic domains start to get close, they can actually now overlap. And one phase we have is 1 skyrmion on one layer and ferromagnet on the other layer, or 1 skyrmion on one layer and a spiral on the other layer. And this one is a little bit tilted ferromagnet. Any questions? Yeah, so D is the strength of the Jalishinsky-Morier interaction, and J is the Heisenberg interaction. And D depends on which substrate the system is sitting on, because of this comes from inversion symmetry breaking. And depending on the substrate, it can vary, and it's very hard to estimate from first principles. All right, okay. So let's see how it matches with the experiments. So the MCD experiments, MCD is magnetic circular diachroism, which measures the Z component of the magnetization, finds that at high twist angles, it's a ferromagnet on both layers, and low twist angles, the magnetization drops down to about 0.6 of the maximum value. So if we compare that with our results, we find something quite similar, that in our case, this this drop happens at 4 degrees instead of 3 degrees, but it's good enough. And at low temperature, at low twist angles, the magnetization saturates to about 0.6, similar to experiment. And also, I should mention that this is a log linear plot. So this drop looks very rapid because it's a logarithmic scale. So if we actually plot our data logarithmically, it looks very steep as well. So this is not a proof that skyrmions exist in this system, but our results are in agreement with the MCD experiments. Okay, another experiment from a couple of years back in Science, they did single spin diamond NV magnetometry. So this is what's called quantum sensing. You have a single qubit and which can detect very, very small magnetic fields. And this is a very, very challenging experiment. And the resolution about is about 50 nanometers here. And they argue that if they clean their data, it looks like this. It's up to you, you know, if you want to take it. I'm no expert in this method, but you know, if it's good enough for science referees, it's good enough for me. But this would match with our theory. Yeah. All right, so this was our first project for twisted magnets. Then we repeated the same thing for another material, this alpha ruthenium chloride. And the next ones I'm going to go a little bit quicker because I want to show you a little bit more other things. So this material is a candidate for a quantum spin liquid, but it orders magnetically. And people observe that if you apply in-plane magnetic field, you may get a quantum spin liquid, though it is people still argue about that. And we want to see if we can tune the magnetic phases, not by applying magnetic field, but via twisting. Okay? And Antiyas group again did first principle calculations, obtained the interlayer exchange, and we have done LLG simulations. And this is our phase diagram. But we find that this is the inverse twist angle. So this would be this is the, large twist angles, you have what you have in the bulk. But at small twist angles, you actually get a different type of phase where the different types of zigzag orders coexist. And this arises because of the fact that the interlayer exchange acts as a new way of creating magnetic frustration. So even though we cannot say much about the quantum spin liquid here, we can say that it's bad for the classical order. And in that sense, it may be good for the competition between the quantum spin liquid and the magnetically ordered phase. Questions about this one? All right, so another type of system that we considered are these recent synthetic Kondo lattice systems. So these are 1T, 1H tantalum sulfide or selenite bilayers. So here, the one layer is a multi-insulator and the other layer is a metal. And the interlayer exchange between them can give rise to an effective spin-spin exchange. And indeed, in scanning tunneling microscopy experiments, people observed what looks like a Kondo resonance. Okay, so this gives us the motivation to introduce a Moira super lattice version of the Kondo model. Kondo model is one of the most studied models in condensed matter physics. But now we have two layers where we twist the two layers instead of having the metal and the multi-insulator to be exactly on top of each other. We twist them and see what we get. So in this case, we have two recent papers. The first one, we estimated the magnetic interaction. And what we find is that due to, once again, stacking dependent Kondo interaction within the Moira unit cell, you have different types of magnetic interactions. And this gives rise to complex magnetic textures. This paper. And then we also recently studied the competition between magnetism and Kondo effect in these systems. So within the Moira unit cell, certain regions wants to be magnetic metals, depends on parameters. I'm skipping, I didn't show you any Hamiltonian or anything, but just intuitively, certain regions wants to be a magnetic metal, certain regions wants to be an insulator. And depending on the parameters, if the metallic regions percolate, you have a metal. If they don't percolate, you have an insulator. So you have a metal insulator percolation transition, depending on the parameters, which can in principle controlled by a pressure. All right, so now I'm moving to my second part. So everything I talked so far were more or less semi-classical, and this part will be all quantum, but it's going to be a little bit also math. Okay, so I'm giving you a warning right now. So the last 15 minutes, I can show some math, right? So bilayer quantum spin liquids. So let me tell you what quantum spin liquids are. So these are actually the disordered phases of magnetic insulators. So you have local moments that are interacting with each other, but they don't order. This can sound a little bit boring because normally people try to increase the transition temperature to make devices, not decrease it, right? Why would you try to decrease the transition temperature? But it turns out that if you can completely suppress the magnetic transition, keep in mind that you have magnetic moments which carry an entropy, right? At zero temperature, this entropy has to go somewhere. If they don't order magnetically, where do they go? And the answer is they actually order topologically. Okay? So that's what I'll try to describe. So how can we actually achieve a quantum spin liquid? Normally, everything wants to order. They want to get rid of their entropy, right? They want to order magnetically. So how can you actually obtain quantum spin liquid? One route is the geometric frustration. So if you consider a triangular lattice with antiferromagnetic exchange, so you can put one spin up, one spin down, but the third spin doesn't know if it should be up or down, right? So you cannot satisfy all the bonds at the same time. You can only satisfy part of the bond. So that would suppress the transition. And the second route is the quantum fluctuations. So what do I mean by quantum fluctuations? What I mean is that a qualitatively different classical and quantum states. So to be more concrete, let's consider two spins that are interacting antiferromagnetically. So the classical Néel antiferromagnet has a long-range magnetic order. This breaks time reversal symmetry, spin rotational symmetry, and translational symmetry. Whereas if you solve this SI.Sj, which I do it in my undergraduate quantum mechanics class, but you know that you actually have a spin singlet, right? So spin singlet does not break any symmetry, right? So spin singlet does not break any symmetry. In principle, if you have these spin singlets that are resonating everywhere in your system, you would not break any symmetry, unlike a Néel antiferromagnet that breaks most of the symmetries of the Hamiltonian. So this idea came from Phil Anderson a long time ago, 51 years ago, yeah. And he suggested this for antiferromagnetic triangular lattice. And later on, he generalized this to square lattice as a precursor for unconventional superconductivity. Now we know that after many years, people have done numerical simulations for the two-dimensional square antiferromagnetic lattice, and we know that it actually orders magnetically. So Anderson's proposal was not completely correct. But this idea states, if we can obtain this quantum spin liquid, we can actually, I'll show you that we can obtain new particles. Okay? All right, so for this, maybe I really have to do this part. I have to introduce you the Kitaev model because that's my work is based on, yeah? So bear with me, please. So this is a very simple model that's introduced by Alexei Kitaev on a honeycomb lattice where you have three types of bonds. So every side has three types of bonds on honeycomb lattice. And the red bonds interact with the X component of the spin. The Y bonds interact with the Y component of the blue bonds interact with the Y component of the spin, and the green bonds interact with the Z component of the spin. Right? So it looks a very simple model. But it turns out that this model is actually exactly solvable, which may sound like, okay, I mean, so what? But actually, there is almost no exactly solvable spin model in 2 dimensions. I think the Ising model is one exception, right? You don't even know the exact solution of a Heisenberg model in 2 dimensions, right? So this model is exactly solvable, and it has a quantum spin liquid ground state. Actually, till this model came out, many people didn't even believe that the quantum spin liquids can exist in nature. So how do you solve this? Actually, there's this model is solvable because there are these flux operators, which is the product of the Hamiltonian around these plaquettes. and they commute with the Hamiltonian. Therefore, this gives rise to infinitely many conserved quantities. As a result, the model is integrable. But if you actually want to do a calculation and find the solution, you need to introduce Majorana fermions. So you can represent the Pauli matrices. We have 3 Pauli matrices using 4 Majorana fermions. And the Hilbert space of the Majorana fermions is larger than the Hilbert space of the Pauli matrices. Therefore, you have to apply a projection after you do the calculation. So many of you might be saying, what the heck is Majorana fermion? So let me tell you about them. So Majorana fermions, let's start with the complex or Dirac fermions. So these are the usual fermions that we have, in condensed matter physics, and you use these complex field operators to create or destroy these particles. You may remember these from, let's say, the solution of the harmonic oscillator as the ladder operators. In those cases, those are bosonic, but it's the similar manner. And you want to make the whole fermionic wave function anti-symmetric, therefore they have to anti-commute. Okay, so that's the algebra that they obey. And in 1937, Ettore Majorana, who's an Italian physicist, predicted that if you have a real fermion, meaning that it's equal to its Hermitian conjugate, you cannot, if you have this type of particles where the particle is equal to its antiparticle, then the particle cannot have any mass, right? Because normally so if you have a particle that's equal to its antiparticle, then you cannot have, I don't know if to explain this part, but mainly he predicted for neutrinos. And by now we know that the neutrinos actually have mass, right? So this prediction was not really correct for the neutrinos, but it turns out to be very useful for condensed matter systems. And why cannot they have mass? Because if you calculate the density, it's a constant, okay? Because the density operator is a constant, meaning that you cannot have a mass. All right, so you can write every complex fermion in terms of 2 Majorana fermions. Mainly, the complex fermion will have a real and imaginary part. The real part, you say it's 1 Majorana fermion, and the imaginary part, you say I times the other Majorana fermion, right? So 1 complex fermion is always equivalent to 2 Majorana fermions. This means that if you have a condensed matter system which has Majorana fermions as excitations, as low energy excitations, this means that the system exhibits fractionalization. So this is very similar to fractional quantum Hall effect, wherein, let's say, in a Laughlin state, the electron splits into 3, right? Whereas in this case, the electron or the spin splits into 2, right? The low energy excitations of the system mainly have quantum numbers that are smaller than the fundamental particles of the model. All right. So if you use this Majorana fermion representation and put it in the Hamiltonian, what you would observe is that the Hamiltonian actually becomes solvable. You will have mainly this 3 of the Majorana fermions becomes bond operators, and they commute with the Hamiltonian. So they act as like Z2 gauge fields, because this is either +1 or -1. And then there you have 1 Majorana fermion that's free to move. And in the ground state, this Majorana fermion that's free to move in your crystal becomes has something like a graphene-like dispersion in momentum space, and you have excitations that are gaps that comes from this flipping the other Majorana fermions, which are called the flux excitations. Okay? So this model is as I mentioned, is the first exactly solvable model, and there's a lot of research going into this type of models, because in general, with any other model, you don't have an exact solution. You have to do large-scale numerical calculations, which is very hard, which is very challenging. With this type of models, you can actually have analytical control. So I want to take this and make a bilayer version of it. And it turns out that the moment you make it bilayer, the problem is no longer solvable. Okay, so you actually lose the good aspect. You know, it's solvable, but you make it bilayer, the interlayer exchange does not commute with your fluxes, therefore you don't have any exact solution. And if you do a mean field theory, you get a phase diagram where you go from a spin liquid to a gap spin liquid to an interlayer dimers, where the interlayer exchange just forms dimers between the two layers. And but following exact diagonalization, so a numerical calculation showed that this mean field theory is not very accurate. You actually become a trivial dimer at an interlayer exchange that's about an order of magnitude smaller. Right? So we can conclude that the Majorana mean field theory is not very accurate in this case, because the moment you introduce this interlayer exchange, your fluxes, which were constants of motion, starts to acquire dynamics and move around. And it turns out that that destroys the spin liquid much before than you can capture from the mean field theory. So what is our strategy? We actually use a generalization of the Kitaev model. And so the Kitaev solution relies on the anti-commutation relations of the Pauli matrices. We have 3 Pauli matrices, therefore you can only write Kitaev model for lattices that has coordination number 3. But if you, instead of having a spin 1/2, which use the Pauli matrices, if you have a 4-dimensional local Hilbert space, something like instead of 1/2, a spin 3/2 operator, which has a 4-dimensional Hilbert space, then you can represent the Hilbert space by the so-called gamma matrices that obey the Clifford algebra. These are very similar to the Pauli matrices. There are 5 of them that anti-commute. And as I mentioned that you need the anti-commuting matrices, you can generalize the Kitaev's construction all the way up to coordination number 5 or other models that has higher symmetry. Okay, so that's what we are going to do. We are going to introduce 6 Majorana fermions instead of 4 Majorana fermions. And these can be represented either the operators for J3 spins or 2 types of spin 1/2, like spin and orbital degrees of freedom. And we are using a model that was introduced a while back. So you have both spin and orbital degrees of freedom. And we can use the Majorana fermion representation, as I promised to you, for the exact solution. And in this case, similar to the Kitaev model, you have these bond operators, but instead of having 1 flavor of Majorana fermion, you have 3 flavors of Majorana fermion. So this X, Y, Z are not the real space, but it's just different flavors of Majorana fermions. And we pick an interlayer exchange, now commutes with the Hamiltonian. That's the whole point, right? In the usual Kitaev model, I could not find any term that commuted with the fluxes. In these generalizations of the Kitaev model, I actually can do that. And but this interlayer exchange still becomes an interaction term. And I'm first going to treat it in mean field theory, and then I'll try to justify the mean field theory. And if I do the mean field theory, we find that there's a mean field transition from a gapless spin liquid to a gap spin liquid when the order parameters acquires opposite sign. And we just find that there's no other transition. It stays as a gap spin liquid. There's no trivial dimer phase. And this is questionable because we are doing a Hartree-Fock mean field theory when the exchange coupling is order 1 or even higher. So how can we justify this mean field theory? And what we did is we actually did a perturbative analysis. I'm not going to try to explain this to you, but we can solve this effective model exactly. And the first term turns out its ground state of the first term reduces down to this kind of shapes where these lines obey the Ising version of the Gauss law. And then the last term actually flips these plaquettes. So combining these 2 terms, actually the ground state of this effective Hamiltonian can be mapped to a honeycomb version of the toric code, which is another model of that Kitaev introduced. And usually commonly, people say it's useful for quantum error correction. Okay? So our model in the limit of large interlayer exchange still has Z2 topological order. This way we justify that our mean field theory is valid. Okay, maybe for the sake of time, I'm gonna skip this part. Okay, I'll talk 2 more minutes. Okay. So another calculation that we have done is a different version, again, a gamma matrix generalization of the Kitaev model. And this time it's defined on a square lattice, and the interlayer exchange is an Ising term, which still commutes with the fluxes. So therefore, the intralayer fluxes are conserved. We can use Majorana fermions without doing a mean field theory. And if we do that, we show that the low energy sector of this can be mapped onto a pi flux Hubbard model, which people have studied via quantum Monte Carlo. So this is numerically exact. And what people found that at low interlayer exchange, you have a gapless Dirac semimetal, and this becomes an antiferromagnetic Mott insulator at a critical value. And if we convert these, this is in terms of our effective degrees of freedom. When we convert this back to our original spin and orbital degrees of freedom, what we find is that the antiferromagnetic order parameter, depending on where it points to, gives rise to different type of phases. If it is pointing along the z direction, then this is like a local order parameter. Whereas if it is pointing in the plane, then you actually don't have any local order parameter, but you have a long-range topological order, which is called a string order. And therefore, depending on your spontaneous symmetry breaking, you end up having different types of phases. And in general, the order parameter can point in any direction, which will give you a coexistence of magnetic order and topological order, which in the context of frustrated magnetism is called magnetic fragmentation. And one final thing is, if you look at the low energy excitations of these phases, there's one phase where the the order parameter points along the z direction. If you look at its Goldstone mode, we find that it's fractionalized because it's a bound state of 2 Majorana fermions on 2 different layers, and they carry different Z2 gauge charges. As a result, is a fractionalized version of a well-known particle called Goldstone boson. Okay? So in the experiment, you cannot really create one of them. You have to create pairs of them. And then therefore, even though you have local order, you will not have something like a magnon dispersion. You will have a continuum of excitations. Okay, with that, I'm going to skip the rest. I'm going to just go to my conclusions. Okay, thank you.